So my name is Said. So today's session is a short webinar, short sessions on integrated factory modeling and a little bit of factory simulations, FlexSim. Okay, so everything that is shown in this session is all Autodesk related applications. Okay, if you have question later on, you can drop us the comments and or Q&A or email us back. Okay. So my name is Said, so you can call me Said. If you have questions, I think I need to stop sharing one. Okay, so basically, you can see my screen now. So the goal of today's session is not to show you how to design a factory from basics and all. Okay, so basically, if you are a equipment manufacturers, you designing and building machineries to be placed into a factory floor. Okay, so usually, how do you plan the positions and also to plan the flow or the factory floor? Probably you are using manual AutoCAD drawings or a PDF and place your equipment accordingly. But let's say we step up a little bit. Maybe you want to design your own process, factory process. So how you do that? Okay, based on experience or based on best practice. Okay, so with FlexSim, we can help to show a little bit on how to plan a factory layout from maybe from one station to another. What's the throughput on a station or the whole factory? All that can be so simulate. Okay, so the video that you're seeing here is basically the whole the bigger picture of what a digital factory is. Basically from 2D drawings, planning stages, concept stages to design, planning, process planning, okay, and then coordinations with building and infrastructures. Okay, like in this stage now, we already into the IoTs where we want to see how our factory are performing, how our machine are performing, how our stations are performing. Okay, of course, with this is not just by using software. It also require hardwares like sensors, IoT sensors, and the integrations from the machines to the software or to the models so that we can view live data just from our desktop. Okay. Okay, so what is a digital factory? What is a factory? Everything that consists from building structures and also all the machineries. Okay, so the goals is to go towards smart factory or digital factory. So where we can know what is the changes, what is the project's timeline. Okay, like the one on the left hand side, bottom left hand side, a dashboard of the projects. Okay, and then the one on the bottom right hand side is the how the factory are performing, all this the condition or the situations on the live data of the locations. Okay, so quick one. So the impact of moving towards digital factory or a smart factory. So we want to save, we can save 40% global energy, global water, okay, reduce the emissions. Nowadays is the time of ESG, SDG, where we need to go to carbon zero and so on. Okay, from on the right hand side, from a factory point of view, so you want to keep the operational costs of a factory floor at a minimum, optimum, but minimal cost. Okay, you want to make sure that all the new system or the new floor or the new process are all optimized. Okay. Okay. All right. So now, so a quick view at the landscape. So the technology. So what is it about? So what is related in a so-called the digital factory idea that we are going to focus. Okay, so in today's session, it's not covering everything because everything will take up a bit more time than 1 hour, probably maybe half a day. So if you're interested to learn more, do let us know. Maybe we can arrange a separate sessions to dedicated on your needs and requirement. Probably you are doing a portions of the whole um, thing. Okay, now let's go towards next one. So little factory stage. So usually, so how people are planning a factory, a new factory, let's say a greenfield factory layout. So digitalized for scenario planning, but the scenario planning is never simulate. Okay, so it's just based on what if this happens. It's not been considered. Simulation and risk mitigation. How do you simulate okay, all the risks, okay, physical and digital system connected real time. This is where we're talking about the IoT sensor and all. Okay, so but today's session, so we will focus on the right hand side, so the planning and the design stage only. Okay, we won't talk about the task management. So we will talk about process concept and reality capture. Okay, so let's say you already have a location. So it's a brownfield project. So if you have a 3D model of the location, good. But the 3D models will not reflect the real conditions of the sites. Probably there are some new I don't know, door, maybe a beam, additional beam or partitions are now available compared to 3D model data or maybe PDF layout. Okay, so process concept. So we want to plan our process. So we want to know, so what is the best, maybe what the best machine to use, how many operator that you need to place at certain stations. Okay, what is the distance between maybe machine A and machine B, the best position to place a conveyor. So all that. Okay, so we want to optimize layout to maximize all the throughput and productivity while identify where is the bottleneck. Okay, by bottleneck, I mean the bottlenecks in productions. Okay, so give a quick ideas. So now this is all the very commonly known or very famously known AutoCAD. So it should be look familiar to you, but probably what's not familiar to you is on the right hand side, there is a library of asset called factory asset. Okay, factory assets is all available within Autodesk PDMC and factory design utilities. You have all the libraries. Now we go to FlexSim from that 2D data just now. So I can use the library in FlexSim to place all the related machinery. Okay, now machines and also rack here, and then I put a conveyor. Okay, to imitate or to simulate the real the real life condition of a factory. Maybe this is how I want to do it at first. Okay, from my logic thinking, this is maybe how I want to place the machines, a conveyor. Okay, maybe assign one operator there. Okay, I can create a setup time, maybe from one location to another location. Okay, in this case now, from the source is like, let's say the raw material comes in from that conveyor. Okay, goes to rack first, and then from that, go to processor 1. Okay, and then go to the rack. And then I can also move the raw material to processor 2. So basically, there are two machines that process the raw material or maybe the products now. Okay, and then also I can plan the location of where the operator is. Okay, and then I can simulate. I can simulate the processor 1, processor 2, how, okay, their efficiencies. Okay, now let's say I change the layout a little bit. So instead of using man as operator, I use robot arm. Okay, and then I change the position of the machines, the conveyors a little bit. Okay, so now we can see, let's just go here, the differences with just that minor adjustment. Okay, so from before, which is using one operator, so we can see the average stay time. Basically, the person or the operator go take the equipment or the parts, go put in in the machines and then wait for it to move to conveyor. So that is what I call a stay time. This is what I set as stay time. So by just changing it to robot arm and then rearrange the position of the two machines, only by that, so we reduce a lot of the stay time, okay, and also reduce the maximum stay time. So this person or this operator will not stay long at one place. Okay, so from this, we can just get a shorter average waiting time and also less bottleneck and also optimize the throughput of that stations. Okay, so this is very simple example. Okay, so with and minor changes. So next, let's see. So that is just to give you a little bit of insight of what is factory simulation or process concept simulations. Now, in a condition where we want to plan, we already plan a factory, but we also have the point cloud data. Okay, so the point cloud data, okay, by probably maybe the location of the factory, maybe they use their own 3D scanner or they hire a consultant to do. Okay, so maybe they use all the common brands like Topcon, Leica, and all. So after process, so Autodesk have an application called Recap Pro that will have to process all the point cloud data and clean up whatever is not needed. So like in this screen you are seeing now, so this is the area that we want to focus on because this is the floor, factory floor that we want to use to insert our factory station over here. So now let's just place the point cloud data. So the point cloud data that was just processed, we can put it into Inventor. So this is the Autodesk Inventor interface. Okay, so let's just place it. You can see that now I can control, I have a control of the point cloud data. I can hide, suppress whatever I do not want. The point cloud data also behave like an 3D object where we can measure, we can use the point cloud data to measure from, let's say, from the pillar to pillar or pillar to the machines to check on clearance. Okay, this can be done. So it's very, very, you can reduce a lot of time if you have or request a point cloud data or a 3D model from the client or from the factory. So, but if you do not have this, okay, example, let's say you do not have this, you have to work with whatever that you have, maybe from AutoCAD drawing or PDF also. Okay, so now after putting in the point cloud data, now I'm putting in my platform structure there to see, and then later on I can check for clashes. So that is on the next stage. Okay, so done with that, the first two parts. So on the plan part where I just focus on process concept and reality capture, I did not show task management because task management example is just like how to separate out the tasks, okay, assign a task to maybe departments or teams or contractors, okay. Now let's go back to, let's just go to design part. So optimize a factory design, okay. I believe everyone are familiar with their own machinery, their own equipment, but to plan a layout is another thing where you need to know the locations, the positionings. Okay, so whatever is shown is all from Autodesk product design and manufacturing collections. Nothing is outside from this package except the FlexSim, which is later on. Okay, so if you have this or maybe you're interested to know some of this, do let us know. Okay, so for this case, let's say this next example is just focusing on these four, which is Inventor Professional, AutoCAD, Navisworks Manage, and Factory Design Utilities. Okay, and a little bit of convergence because, of course, you have building, maybe your client or your contractor, the building contractor, they have BIM format or Revit files. Okay, Revit and also Inventor can work in collaboratively well together. Okay. All right. So what's good about Inventor is Inventor are able to open and process a lot of file formats. Okay, open directly with any CAD technology where it will not convert, but instead it will open. Okay, So, and what are the factory design utilities? Okay. So in the earlier video, the first video, you see that AutoCAD have libraries of machines and conveyors. So where is all these libraries come from? All these libraries come from the factory design utilities. Factory design utilities works inside AutoCAD, inside Inventor, and inside Navisworks. As you can assume it as a plugin for all these three. Okay, the right bottom part of the screen, you can see this is the libraries of factory assets. Okay, human transportation related material handling machines, conveyors, vehicles. Okay, all is there. So if you are a industrial machinery manufacturer, you want to add your own machine inside the asset, you can do that as well. Okay, they are processed to bring in, to make your equipment as an asset so that it's easier for you to use next time, like a Lego. Okay, so now we go back to our AutoCAD. So this is common 2D layout. The right hand side, you see that I have asset browser over here. This is all the libraries on the right hand side. Now I'm adding in fixtures. Okay, so maybe I want to add some welding cells. I just take from the libraries. So this is standard libraries. Okay, and then maybe my platforms. Okay, so what's good about this asset is if this is created with Inventor, we can control all the parameters of the equipment. Let's say you want to change the size, length, height of your equipment, you can do that. But if, let's say, the equipments you receive are not Inventor format, let's say from CATIA or SolidWorks or what other file formats, also no problem. You can also add it into the asset library, just that you cannot control on the size. Okay, let's say you require a multiple size, you need to load multiple files. Okay, but not be worried, because it's not uploading the whole equipment, but instead it's a simplified version of the equipment. Now, let's say I want to adjust the positioning, the angles, so I just do that from a browser. Okay, so it changes the length because all these are created with Inventor, so I have full control of the components and machinery and also the layout. Okay, so adding a cell there. Okay, so after we add this all in 3D, so this is a 3D environment, right? So this is Inventor. So let's say I make some changes, okay, and then let's say I sync up later, so it will also update in AutoCAD. So AutoCAD and Inventor, so in this scope, it relate to each other, so they have associativity. So let's say one changes happen in the AutoCAD or in the Inventor, it will reflect both sides. Okay. All right, so that's on the 2D to 3D design. So very quick explanations. Okay, so just recap a bit on the 2D to 3D workflow. You have 2D, you have the 3D models. Next is just using the factory asset so that it will reflect in both environments. Okay, they are always a link. Okay, so this is again an overview of how it looks like. You can see more libraries asset on the right hand side. Just click and place, click and place. Okay, so let me just place it. Okay, and then add a conveyor there. So okay, so it's not conveyor. So this is the safety fence. Okay, so we added safety fence in AutoCAD just now. So now in Inventor, it will auto reflect, and see it now showing the conveyor and also the cell fence that we created in AutoCAD. So that's how it performs. This is how it behaves. Okay, associatively between the two. Okay, so if the equipment is done with Inventor, you even have the capability to automate it. Okay, with the size, or let's say in this case, the door, the opening of the door, and so on. Okay, so earlier I mentioned that we are not loading the full informations of the equipments, okay, of the factory equipments, but instead we simplify it. The left-hand side is the, let's say, the full assembly, okay, 1,582 open documents, okay, 16,000 parts of occurrence, okay. So it means it has 16,000 parts, but after simplified, to put it into the FDU, Inventor can simplify all this. Okay, Inventor is very good at simplifying the big assembly. It becomes just 65 occurrence. It means 65 entity and 37 open documents. Okay, become lighter already. So can put in the libraries easily. Okay. So the object library is central element. So it's centralized. Several thousand objects are available in the scope of delivery. So out of the box, already have several thousands objects. Standard one. Okay. You can also add your own. Okay. So design coordinations. So the collaboration, multidiscipline coordinations. Okay. So we have buildings. Okay. Let's say we have factory and then we have a lot of things. Okay. So the owner usually have the complete buildings and then what is inside that, okay, the aspect that we need to put into consideration. So the building structure, the MEP, the foundations, the steelworks, the envelope door, window, okay, the MEP service, the steel framing contractor. So all this is multi-discipline coordination that need to be done if we are working with a factory floor. Maybe you just, okay, you just do the factory equipment, so the machinery, but you have to work with all these people also. Okay, so that require quite high level of coordinations. Okay, example over here. So this is on Revit. So the building owner. So what building owner can do, they can share you the models. Okay, so they can send over the models via cloud or maybe via time drive. So whatever that you prefer. So in this example, it show using cloud. So sending over the buildings via cloud, okay, and then we can create data exchange from cloud and then just assign whatever need to be assigned. So in this case, just that area for this factory stations. Okay, now we putting in all the building just now. Okay, inserting into Inventor. Okay, so we adding into Inventor and then place it accordingly. So now we can see, oh, it's already there. So in the position, but from here, the visual, I think you can see something is wrong somewhere. Okay, you can see the steel structure over there is actually hitting the so-called wall, the opening. Okay, so what we can do, we need to ask the owner to maybe give us the data or make some changes to the opening. Maybe increase the opening a little bit. Okay, this one like screenshot to create markups to inform that, oh, this need to be changes. Okay, headroom only, okay, need to increase the headroom. Okay, so now, so the designer or the modeler, so they are using Revit, so they just increase the opening a little bit to make sure that there's no clashes. Okay, very simple edit. They just save in Revit, so in Inventor, we do not have to open again. So basically just click update. So it automatically update. Okay, you can see it automatically update. The building automatically updates in Inventor as well because it's linked through cloud. Okay, so this is the data exchange, the strength of Inventor and Revit because you are in between both worlds now. Okay, clash detections. So you can do clash detections. There are multiple ways. So usually people just use Navisworks, but also can be done via cloud. Okay, I'm not showing the clash detections, but instead the example of building integrations. The integration of Revit and IFC, so you can use these two formats. Okay, technical building equipments, buildings. Okay, the workspace, you can simplify it as just a space. Okay, if you don't want to share the whole building. Okay, you can sub it from building, we just apply to productions, planning. Okay, the integration from Revit or to Inventor, Inventor to Revit. Okay, So this example, we are adding in the building again inside Inventor. Okay, so we can simplify whatever need to be simplified. And then let's say import the completed building, the detail one. So we now have a proper factory. Yep. Hello.
Oh, Mister, ya. Okay, boleh. Okay.
Okay, maybe I'll mute you. Okay. So collision check. So building integration collision check, we can do clashes since we're already integrating the factory. Okay, so with the Revit file formats, so we can check all the clashes, okay, like the previous example, or we can use Navisworks to run and see. In Navisworks will inform you where is the clashes. Okay, so this is done by Navisworks. You can see Navisworks will tell you what is the part that are clashing. Okay, even though you can see on the left-hand side, selection A, all that is all separate files. Okay, so selection A is running versus selection B to see the clashes. Okay, so this way we don't have to look visually, so it just run and tell you that there is clashes somewhere. Okay, so now on to also looking at the chat box and also Q&A. If you have question, you can type it there. Okay, optimize factory designs for factory simulation. Now we focus on factory simulation a little bit. Okay, so this is how a FlexSim looks like. On the left-hand side is all the libraries. Okay, so you want to use operator, source, queue, conveyors is all on the left-hand side. The right-hand side is how you control the thing that you selected. Like in this case, now I'm adding in a robot arm. On the right-hand side is all the setting that we can control the robot arm. Okay, maybe the size of the robot arm, the height, okay, how it move. Okay, so you can see the factory is simulating, so we can see the movement. Okay, so here we can also simulate how fast maybe the warehouse will be populated versus time. Okay, and then how long does it take to move all that barrel from the stations or from the conveyor to transport to a proper storage. Okay, so the right hand side, you can see the status, the machine status of how this factory is performing, how the robot arm are performing. Okay, so where is the bottleneck? You can track the bottleneck is now at the conveyor there. Okay, so maybe one robot arm is not enough. Maybe you need to add one more, for example. Okay, so you can set the goals. How long will it take for 1,000 barrel to be moved into storage, for example? So also on the right hand side here, you can see filling machine status is only operate at 52.94% capacity versus the one on the bottom where 90% capacity. So there are the differences here. You can see from moving the barrel by the transport or by conveyor, which one is faster, which one is more efficient. Okay. So this one you can simulate. You have a result to when you create a proposal, you have a result to show. Okay. Or maybe you want to simulate maybe your machine's operation time. Okay, like in this case, we want to pack I don't know, maybe box or packaging machines. How long will it take from one station to another to complete a full box of I don't know, maybe that's a flour or sugar, for example. Okay, so you can simulate that. Real time, we can plan how fast the movements. Okay, so this is good when you want to show how the factory performs. So there's two benefits here. So to show how the factory is moving, how the factory is working, and also the performance of the factory floor. Okay, you can create multiple options and compare the few options that you just created. Okay, design review, improve collaborations. Okay. Okay, so nowadays it's all the digital time, so where you can share the design via clouds, VR, AR. Okay, so all that can be done if you digitalize the whole factory. Okay, just an example. Okay, so that's on the two parts, so plan and design. So very quick one. And then let me just go to a FlexSim. Quick one to intro a FlexSim. FlexSim is a simulation software for factory flow. You see the some of the example earlier. Okay, it is called discrete event simulation. It's not simulating maybe it's not simulating the strength of the steel, okay, the performance of a material, no, but instead it is simulating all the variable of how a machine or a factory performs. Okay, representation or real life system. Okay, you can simulate a system or a process. Okay, you can evaluate whatever ideas that you have before implementing. Okay, you can run what if simulations. Example, like earlier example, we are comparing using an operator, a person versus a robot arm. Okay, so what is the benefits? How long is it takes for both to complete the same task? Okay, okay. So it works well with 2D layout and also 3D models. Okay, all that is needed to create the factory simulations. Okay, it simulates the flow of any process, manufacturing, assembly, material handling, people. Okay, so why do you use these applications is because to prove, let's say you want to propose a new factory layout. Okay, but you do not have a reference how it performs. So you can use FlexSim to show how it performs. Optimize existing production process. Okay, for example, earlier we're talking about a new process. If you want to optimize an existing process, we can also do that. Okay, make accurate plans to solve production issue. If you know, you want, let's say now in real time there is some bottleneck. You know there are some bottleneck at maybe a few stations. Okay, so how to improve that bottleneck? So instead of investing on something that probably not you cannot optimize, maybe you can plan and simulate first. So when you do this, you have a better and clear picture on how to channel the investment. Okay, should you invest on a conveyor, or should you invest on transport, or should you invest on a robot arm compared to more operator? Okay, some examples when can simulation help to test AI option, to visualize a flow. Okay, for safety and all, optimize and validate changes. Okay, so some of the strength or type of libraries that FlexSim have is conveyor. So it have all these conveyor types, okay, common conveyor types that you can use ready to go out of the box. Okay, let's say you have a storage system, you want to plan a conveyor. Okay, you can just use it like Lego, put, drag and pull. So warehousing. Okay, so all the libraries for warehousing related, racking, storage system, okay, paint labels. Okay, for electronic manufacturing, in case you are in electronic manufacturing, so what can it simulation helps? So validate and optimize electronic manufacturing. Okay, should you add 1%, 2%? Okay, understand staffing requirements. Let's say you want to rework the models. Optimize warehousing, link your warehouse system to WMS to model actual data and order versus order. You want to model complex material handlings, visualize better in 3D, in VR, process the flow logic. Okay, vehicle modeling. So you want to plan a vehicle, a transport in a factory. Okay, so you want to plan their movement. You know, their movement need to be, example, the image on the left-hand side. So the movement need to be programmed. Okay, how do you program? Okay, what is the models of the AGV that you need to invest? Okay, what is the size? More importantly, can it fit your floor? Okay, And then FlexSim AGV. So this is similar to AGV. It's now automated guided vehicle. So we can plan the where it will move. Okay, example nowadays you see a lot of this thing like the robot at Mama shop, right? They're sending in drinks, food. Okay. Similarly, they need to plan the direction, the movement. Okay, so this is also a way to plan. So is it safe for them to go towards this direction? This is all need to be counted in the simulations. Okay, we talk about machines. Now let's talk about people. People flow. So if you are familiar with how a factory looks like, so usually you will see things like arrow on the floor. Okay, so walking area. Do not walk at outside of this area because of what? Because there'll be a lot of transport moving in and out, AGVs moving in and out. So maybe that is the hazard area. Okay, so all that can be planned and simulate. Okay, you can plan how people will work, how people will move also, the movement of people. You can simulate maybe using, let's say, from station A to station B. So what is the best path to use? Shortest and fastest path. So all that can be simulated as well. What happens when two people are colliding with each other like this? So they are meeting each other on the same path. So do they have room to move? Okay. Okay, so you can also use FlexSim to simulate a process where when people interact with something like in this case, they want to send the patients to to the bed. Okay, which is the best path? So the component that you can set here, play around here is like the location, the staff, the equipment, the transport. Also, good, let's go a step up. So the GIS navigator, you can simulate also the transport, let's say from Port Klang to maybe Ipoh Perak, for example. Okay, so we can also simulate the direction, plane, train times, points on the map. Okay, so let's say you're doing logistics, so you want to plan. So let's say, example from Port Klang to Shah Alam. So which is the best route? Route A, route B, route C. So all that you can be simulated. Okay. Okay, also FlexSim allows the user to create what if scenario. What if scenario is something that you can add just what I call a parameter or the factor that may happen. So
to make this system more realistic, we can add an operator to the model. To do this, find the operator in the library under the Task Executor section and drag the operator into the model near the queue. The operator needs a link to the queue so parts can be carried to the processors, so we'll need to make a center port connection. The center port connection is used to communicate between the fixed resource, the queue, and the task executor, the operator. In this case, the communication will be to send a task sequence to the operator to travel to the queue, load a box, travel to the processor, and unload the box. The walking speed of the operator and the distance between the queue and the processor will determine the time it takes to travel between the two objects. Hold the S key on your keyboard, then click and drag the mouse from the operator to the queue. You should see a visual indicator showing a line that connects the operator to the queue. To get the operator to move the boxes, click on the queue, go to the output properties, and check the box to use transport. Once checked, you will be able to see the reference from the current object, the queue, to the object connected to the center port 1, center objects 1. When a box enters the queue, a task sequence will automatically be created and sent to the operator that is connected. Before we run the model, include the operator to the state chart so we can analyze their utilization. Hit reset and run the model for an 8-hour period. You can see that adding the operator to move the box has had a major impact on the system. Wait time in the queue is 2,842 seconds. Average processor utilization is 79%. Average operator utilization is 54%. It's interesting to note that none of the involved resources, the processors or operator, have a utilization above 79%. Yet, there is a major bottleneck as the queue has backed up with hundreds of boxes. We know from the previous scenario with no operator that the system was working with no bottleneck. We know that the only change was adding one operator. So let's use the model to investigate the impact of adding one operator. The first step is to run the model and watch the simulation animation to see if we can observe anything that might be impacting the throughput. Reset the model, slow the run speed down so we can see what the operator is doing, and run the model. Notice the default behavior of the operator. He does exactly what the task sequences tell him to do. He travels to the queue, loads the box, travels to the processor, and unloads the box. At that point, he either waits at the processor for the next box to arrive at the queue, or he travels back to the queue to pick up the next box. Immediately, we see that it's important where the operator stands to wait for the next box. If he stands by the processor, the box must wait for the operator to travel all the way to the queue to pick it up. We could save this wait time if the operator was waiting by the queue for the box to arrive and could immediately carry the box to the processor. How important is the place where the operator waits for the next box? Let's find out. We can tell the operator where to wait by using a trigger on the operator. Select the operator, go to the Properties panel, and scroll all the way to the bottom of the panel. At the bottom, you will see the Triggers section. Just below the heading, you'll see a green plus sign. Select the plus sign to find several options in a list. This is a list of triggers that are fired when certain events occur on the object. Select the on-unload trigger, which fires whenever the operator finishes an unload task. For example, when the operator drops the box off at the processor. Just to the right of the on-unload trigger field that was just added, you'll see a green plus sign. Select the plus sign and then select the Travel to an Object option to tell the operator where to go when he drops off the box. There are three fields: destination, priority, and condition. The default destination sends the operator back to the object that is connected to the operator's center port. Since the operator is connected to the queue, and that is where we want the operator to wait for the next box, we can leave the default in place. The priority field can also stay default, since no processor has priority of any other. The condition field needs to be changed to 1, since we want this condition to be true every time a box is dropped off at any queue. Rerun the model by selecting Reset and then Run. Speed up the model to quickly run 8 hours of model time. Here are the results. Wait time in the queue is 2,021 seconds. Average processor utilization is 85%. Average operator utilization is 60%. We can see that the wait time in the queue dropped about 29%, and utilization is up for the processors from 79% to 85%. The operator utilization increased from 54% to 60%. It's an improvement over the previous scenario, but it didn't solve the bottleneck. At this point, what do we know about the system as it currently stands? Processor utilization is less than 90%, not the cause of the bottleneck. Operator utilization is less than 90%. This tells us that adding more operators to the model will give us little benefit. Adding operators is only recommended when operator utilization is over 90%. The only other variable we added to the model when we added the operator is the travel time of the operator. We just proved that changing where the operator stands to wait for the next box has an impact in travel time, which in turn has an impact on the throughput of the system. Travel time in any system is a serious consideration. What options do we have to reduce the travel time between the queue and the processors? We could move the queue closer to the processors. We could add a material handling component, such as a conveyor, to the system. We can use a Kanban system or batch flow technique. We can add automation to the processors. And there are many other options we could consider. Moving the queue closer to the processor could provide another incremental increase in production, but there is no way to eliminate much of the travel needed to service all three machines. Adding material handling is a viable option if the volume of boxes can justify the cost of the hardware, programming, and maintenance of the conveyor system. Kanban and batch flow are common techniques that are low cost and effective, and they would pair nicely with an automation solution. For example, using batch flow to feed an automated feeder on the processor could be an effective approach. Because of the cost, it's decided to try a combination of batch flow and automation to solve the problem. To model this, all we need to do is add a single queue at the processor where boxes automatically feed into the processor. The size of the queue will determine the size of that batch. We will start at a size of 1 and see how the model performs. To make the change in the model, disconnect the output port connections from the queue to each processor by holding the Q key on the keyboard and click and drag from the queue to each processor. Add a queue by each processor and give the queue a max content of 1. Connect the new flow by holding the A key and click and drag a connection from the original queue to the new queue by processor 1, and then connect the new queue to processor 1. Do the same for processor 2 and 3. The operator will now carry the boxes to the queue in front of each machine, and then the boxes will be fed into the processor automatically from the queue. Hit reset and run the model. Here is the output. Wait time in the queue is 47 seconds. Average processor utilization is 90%. Average operator utilization is 70%. In the first example, we lowered the utilization of the processors to lower the wait time in the queue. In the second example, we raised the utilization of the processors by eliminating the effective travel time to lower the wait in the queue. Utilization plays a vital role in the optimization of any manufacturing, material handling, or process system. Simulation plays a vital role in understanding utilization and the tug-of-war the 3 types of waiting times have on the cost of the process. To make this
Okay, all right. So some of the things that can be solved with FlexSim. So all these variability processes and productions, okay? So lack of understanding the interaction between system and process and also the operators. Okay, high costs because due to process inefficiencies, but how do you prove the process is inefficient? You can use FlexSims to simulate. Okay, inability to understand the potential long-term scenario. Okay, you can also plan for long-term analysis. Okay, risk involved with trying new things. Okay, so let's say you have some crazy idea. You want to try new things, but the crazy things that if you do it in real time, probably there are multiple of risks comes with it. But with FlexSim, you can run it without all the safety or whatever risk that is available in the real world. Okay, so almost end. So conclusions. So why does it matter? Okay, so you can coordinate layout decision across disciplines. You can streamline handover and approval. You can avoid a lot of reworks, reducing delays. Okay, why need to plan in 3D and not in 2D, PDF or Excel, whatever you are using now? Okay, you have better clarity, better visualizations, increased accuracy, enhanced simulation analysis, cost saving. Okay, right. So the key capabilities again, quick and agile block layouts. You basically use it like a Lego, drag and drop, pull between points and also positions. Okay, accurate layout for equipment processes. You can set the parameter for all the equipment and processes. Okay, asset library is available for easy, intermediate, and also advanced or flexible layout creations. Unified models, so you can foster collaboration between the planner, decision maker, and also from the design. You can always use your AutoCAD drawings or Inventor models to start with the planning. Okay, validation and visualizations. Okay, so when it is best to create facility layouts or plan? Okay, obviously it's on the early stage of planning. When you plan for major technology shift, like maybe you want to add new automation systems or new robotics, okay, this is the very best time to start the process analysis. Okay, so when the company direction want to focus more on cost, quality, okay, adjust all the operational efficiency and compliance changes to prepare for growth. Maybe company want to grow, so the factory want to expand, okay, extend extend to maybe plant 2, 3, and so on. Okay, so you can plan the movement or the changes in layout between the few plants. Okay, right. So effective facility layout planning to increase productivity, of course, reduce the design time, optimize space utilization. We can plan for proper spacing, reduce carbon footprint. Okay, why it is important? Because now to comply with the ESG, so all these are taken into considerations. Okay, to improve resource allocations. Like I said, are you hiring too much operator or too less operator? So how do you know how many people that you need? Okay, stimulate by simulating the things. Okay, let's see if there's any questions. Anything at the chat box? Okay, I didn't see anything. Q&A. Okay, so I don't see anything for now, but it's okay. So if you have any question or you want to have a separate session to understand better, so do drop us an email or do inform us so that we can arrange separately. Okay. Okay, since there's a few people in here, so just want to okay, so just want to share that next week we also will have another event. So this is a live event in where is this? In Shah Alam. Okay, in case you are in Shah Alam or anywhere nearby and required to, or you want to collect CIDB CCD point, okay, do register and do attend the event. So you get the 5 CCD point for free with all the foods and AutoCAD related events, more towards construction. But if you are in this field, you see this is like a gray area between the two industry. So please free to register. So maybe Blue, you can put the link, registration link at the bottom part also. Or maybe I can do that.
Yeah. Already shared, right?
Yeah, so registration link also there. Okay, so you can join in. All right, so since there are no questions, so I think we can end the session. So thank you everyone for attending. Okay, hope you gained something today. Do let us know if you require more information or separate sessions. So thank you everyone for attending. Okay, see you again in the next one. Not sure when will that be again. Okay, all right, thank you everyone.